So welcome to today's second session on 5G security by Dr. Mahendra Pratap Singh of NIT Suratkal. Dr. Mahendra Pratap Singh holds the position of Assistant Professor in the Computer Science Engineering Department at National Institute of Technology, Suratkal, where his career started since 2009. His remarkable academic journey includes BTech in Computer Science Engineering, an MEE in Computer Science Engineering, and a PhD in Computer Security, all earned from prestigious Indian Institute of Technology, Kharagpur. Dr. Singh is a senior member of IEEE and holds esteemed membership in ACM and other technical societies. His research focuses on computer security, system security, data security, and network security, where he has made significant contributions to advancing knowledge in this area. His impactful research is published in respected in international and national journals and conferences. Notably, his endeavor have received recognition and support from various governmental agencies, a testament to the relevance and significance of his research in addressing contemporary security challenges. In essence, Dr. Mahendra Pratap Singh emerges as a stalwart in the field of computer security. His dedication to excellence and his innovations contributions paving the way for safer and more secure digital landscape. With this brief intro and bio, I invite Dr. Mahendra Pratap Singh to share his insight on 5G security. Dr. Singh, over to you. Please go ahead, sir.
Thank you, sir. Thanks for the nice introduction. Can you hear me? Can you just confirm, Sanjay, sir, am I audible? And as well as
Yes,
my
sir. Yes, sir.
slide is moving?
Yes, the slide is also moving. You are audible very much.
Okay, fine.
Go ahead, sir.
Okay. Good afternoon, everybody. As Sanjay sir has already given my brief introduction. So I work in the area of security. And in today's session, I'm going to give some brief about the security requirement of 5G. I'm not going to, let's say, bring so many cryptographic steps because I know very well most of the participants are from electronics background. They may not be able to, let's say, get into it in one single session. So instead of that, I'm planning to focus on, let's say, identify the components which need attention with respect to security, and then give some brief about that, how it is addressed, how it was addressed in the 4G and how it is addressed in 5G. So if I'm talking about, let's say, the overall presentation, so mostly I'm planning to cover two major things. First thing is I will try to give introduction of, let's say, the security architecture. I will also talk about, let's say, a piece of information or maybe a piece of, let's say, the entity which we used to call as a SIM, which we used to insert inside our mobile phone. Most of us are having that particular information or piece of entity in our mobile phone, but are not familiar with how that particular piece of information, let's say, helps service providers to uniquely identify a particular customer. And then, I will identify some security concerns, and then we'll see how we can address those security concerns in 4G and as well as in the 5G.
So sorry for the interruption. There is
Please,
a
sir.
background noise is coming. Can you stop that?
Sanjay, sir, can you do that?
Yeah, thank you, sir.
Okay. Sanjay, sir, would it be possible for you to mute this Ishan Ayush participant? His mic is, I hope so, unmute. Because of that, there is some disturbance. Fine. So this is the security architecture, which you can find in the 3GPP version 17 document. And this particular document, identifies the need of security at the various level of this overall 5G setup. So when I'm talking about the various levels, so before, let's say, getting into this particular topic, which speaks about, let's say, the security architecture, let me come back to the normal scenario and then try to identify the requirement of the normal scenario, which is irrespective to the 5G architecture, and then I will come back to the 5G. So let's say in the normal scenario, whenever we are using internet, so what we used to do, we will open a browser, because browser is an let's say the interface by using which a user can interact with the service hosted by various, let's say, service providers at various locations. So the very first thing what we used to do in the browser is we used to type the, let's say, the unique address by using which we can access that particular service. So when we are typing that particular address, then when we press submit button, a request used to be generated, and then request used to get transmitted from one place to the another place, or from to the, let's say, the service provider. In between, whatever the network is there which is used to transmit this particular information may or may not be in our control. And if that is the case, then there are various possibilities. So what are the possibilities are there? So one of the possibilities is that the original message will never reach to the, let's say, the service provider. Another possibility is that someone will capture that original message and will try to behave like you, and will send this message to service provider, and then will get the information from the service provider, and then he will transmit that information to you. Otherwise, what will happen? Somebody else will try to act as a service provider and will try to steal your information. So more or less, what I'm trying to tell here is, see, when we are going to communicate with somebody, before starting communication, what we are supposed to do, we need to make sure that we are going to communicate with so and so only on the internet. So if I'm talking about, let's say, in the current world, what we are doing is we are using the certificates which are named as X.509 certificates. And with the help of these certificates, we will try to validate two things. One is we will try to validate the, let's say, the authenticity of that particular, let's say, the URL, whatever the reply we have received in for a particular response is received from the so and so service provider only, not from the anybody else in between. So which means authentication is one of the property which need to be ensured before starting the communication. Second thing is, in some of the cases where service provider is supposed to authenticate the user, supposed to make sure that he is communicating with so and so user only. So it means the another side authentication is also required. So that is why we used to talk about one-way authentication and the mutual authentication. Similarly, when I'm talking about the transmission of the information, so as I said, the information will be transmitted by using the partially controlled network. And if that is the case, if the network is not in our control, then whatever the, let's say, the security or the claims of that particular networks are there, we have to rely on that. So if network says that I'm providing so and so level of security, yes, we have to rely on that. And as well as network will also provide some sort of way to prove that or to verify that whether that sort of security is there or not. That is one thing. So then we have to rely on that. And if that is the case, then what we are supposed to do it, we need to encrypt our information, and then we need to transmit that information from our end, okay, to the other end by using the network. In between, if some network related security features are also there, so then they are further going to wrap that particular information, means they are further going to encrypt that piece of information, and then they will use their network to transmit the information, and at the other end they will do the reverse of that. So if I'm talking about this particular architecture, which is named here as a security architecture for the 5G. So if you see here, if you are talking about 5G, what we have a, let's say, the mobile equipment or mobile entity. We also have a serving network. We also have, let's say, the home environment. Fine. And if I'm talking about, let's say, the mobile entity, so nowadays, we have a lot of applications installed in our mobile. Similarly, if I'm talking about, let's say, the serving network or maybe the home, let's say, the environment, in the last few days, we are going through this entire 5G workshop, and we came to know across so many functionalities which are supposed to be there in order to enable a user to, let's say, do a communication by using this particular network. So now the question comes, what sort of security is required? So let's say if I'm talking about a SIM, which we are supposed to insert in our mobile equipment. Okay, so first of all, whatever the SIM you are going to insert inside your mobile equipment, we need to make sure that that particular SIM is a valid SIM. is not a entity or is not a, let's say, some sort of information. By inserting that, that will give the control of your device to somebody else in case if you are using some sort of, let's say, the maybe the manipulated or the modified SIM, not the original SIM which is provided by the, let's say, the service providers. So if I'm talking about, let's say, the security between the mobile entity and the USIM. So we have a SIM and here I'm writing a USIM. So I will also talk about what is the difference between the USIM and SIM. So then we, what kind of security we require. So basically here we require the network access security. So when I'm talking about the network access security, what the security will do, this security will enable user equipment to authenticate, fine, and access services via the network securely. This includes 3GPP access as well as the non-3GPP access also. Fine, which means, this particular network access security is required to protect against the attack on the radio interface. Fine, because we will insert the SIM and then this SIM will enable us to connect with the base station by using the radio network. Fine. This also includes the security context delivery from your service network to the AN for the access security. Now, if I'm talking about the AN, so here AN stands for, okay, so, okay, fine. So, okay, it's network, fine. So now, so wherever this one is there, so this one speaks about, we are talking about the network security, network access security. Similarly, the second point, which is written here too. So this particular point speaks about, we require the domain network security, which means, we require some set of security features. And with the help of this set of security features, we will try to ensure the network nodes security, by which network nodes can securely exchange the signaling data and the user plane data. So obviously, as you can see here, this service network is going to exchange some sort of, let's say, the signaling data and the user plane data with the home environment, as well as this particular component is also going to share some sort of information with the service network, and that information will include signaling data and the user plane data. Fine. Apart from this, we also have the user domain security. So if you see here, this mobile equipment and USIM, fine. So what is this user domain security is? So what the user is doing? So user, access. So we require some sort of security features, and these security features will secure the user access to the mobile equipment. Fine. So I said you are putting SIM inside the mobile phone. Make sure that SIM does not contain any vulnerability. Otherwise, what will happen? Your mobile device will compromised. And if your mobile device is compromised, you may lose the control of your device also. Next, what you have is the applications. So here at the mobile entity end, we also have applications. At the service network level, we also have applications. And at the home environment level, we also have application. But there is a difference. So if I'm talking about the mobile entity, we have some user related applications. Whereas if I'm talking about the applications which are present on the service network or on the home environment, they are there in order to provide, let's say, some sort of services. So again, we require some security features, and these security features will enable these applications in the user domain and applications which are there in this, you can say, service provider domain, fine, to exchange messages securely. Again, see, so this is the security level which we require here. Apart from that, we also have a one sort of security label, which is represented here by using this 5. So this speaks about SBA domain security. So here the SBA, this stands for service-based architecture. So we require some set of security features. This will enable network functions of the service-based architecture to securely communicate within the service network, which means within SN domain, and with other network domain also. So which means, whatever the information we will try to exchange, before exchanging that information, we should make sure that we are communicating with the right entity. And when we are exchanging that information, we should ensure the safety and security of the information, because the information will be, let's say, that transmitted by using a network which may not be in the user's control. Fine. Apart from that, there is one more security requirement which is not present here in this particular diagram, maybe included in the coming releases and also. So this is named as a visibility and the configurability of the security. And this visibility and the configurability of security, so this set of features will enable the users to be informed whether a security feature is in operation or not. So many security features are there, whether they are working or not. So that sort of assurance is also required. So as of now, this feature is not, let's say, there, but it will be included. So this will give some sort of assurance of that. Fine. So these are the places are there where we require security. So when I'm talking about the security, I will try to simplify this security by using 3 security properties, which those are authentication, confidentiality, and the integrity. Okay. So when I'm talking about the authentication, so let's say if mobile equipment is going to communicate with the serving network, make sure the mobile network is, or mobile equipment or the user equipment is communicating with the service network only, and the vice versa of that. Similarly, when service network is communicating with the home environment, so make sure there is assurance, or there is a way by using which we can prove that yes, service network is communicating with the home environment only, which means nobody else in between can come and sit and can impersonate himself as a home network or the service network. Because if that is possible, then what will happen? Some sort of man in middle attack scenario will come, and where, knowingly or unknowingly, we will disclose our information to the unauthorized person. Fine. Okay. So, and the last one is the integrity, which means whatever the information is exchanged, make sure that is not modified in transit or maybe at the receiving end also. So the question comes, let's say if I'm talking about this particular thing. So what is the, okay, so the question comes here is, what is the, let's say, so these are the some of the, let's say, the security entities are there which we are going to use it. So let me just come to this piece of information, because as we saw, we are going to insert this piece of information inside the same, inside the user equipment or the mobile entity, and then only this piece of information will enable us. So what is this piece of information? So I'm talking about a SIM card. We all are familiar with this SIM card, and we'll see some sort of a small brass chips. Okay, this chip stores, the subscriber information and is named as a subscriber identity module. Fine. Now, if I'm talking about this particular module, fine. So what this particular module contains is, this module contains, if you observe here, is a processor. There will be an operating system, okay, with between 16 to 256 KB of persistence. There will be some sort of electronically, erasable, programmable, read-only memories we used to call as EEPROM. Fine. It also contains random access memory and read-only memory. So we all are using computers, and we all know the importance of this kind of, let's say, the memories. So if I'm talking about the RAM here, the RAM will control the program execution flow, and ROM will control the operating system workflow, user authentication, data encryption algorithms, and other applications. Fine. So now if I'm talking about SIM, we have this kind of information inside the SIM. So we'll say SIM, how the SIM organizes this information. So the SIM organizes this information by using some sort of hierarchical file system, which resides inside the persistent memory and stores data such as the name, phone numbers, text messages, network service settings. It depends on the phone used. some information on the SIM may coexist in the phone memory also. So if I'm talking about, let's say this SIM, so I said, so this particular SIM contains these many information. So the question comes here is, if this is the case, so does this particular SIM is unique to everybody? And if that is the case, then how this network operator can uniquely identify them? So every SIM is identified by using, some sort of identified internationally by using some sort of unique number. What is that unique number? So that unique number is ICCID, integrated circuit card ID. This integrated circuit card ID, is stored in the SIM card, and it may be printed on the SIM card body during the personalization. Fine. So the number is generally up to 18 digit long with an addition of a single check digit. This will be used for error detection. So this single digit allows us to detect mistyped digits, an input error of the digit, or a permutation of two successive digits. So these digits are calculated. So these digits are calculated by using this particular algorithm, which is named here as a Loon algorithm. Fine. Okay. Now, if I'm talking about this ICCD, which stands for Integrated Circuit Card ID. So the format is something like this. Fine. Now, if you see in this format, so these first two M, fine. So they are constant, and ISO 7812 major industry identifiers. Okay. Here 81, which is 81, this 81 is equivalent to telecommunication administrator and private operating agencies. Fine. So this, if MMM is set equals to 89, this 89 will tell us that this particular ICC ID, okay, is for telecommunication administration and private operating agencies. The next, let's say the two digits which are there in this. Fine. So these next two digits, okay, so they are for the country code. So to identify the country. Then next two digits are there, which are II. II stands for issuer identifier. So now this is used to identify the, let's say the, who is the, maybe the service provider who has issued this particular, let's say the SIM card. So maybe the Vodafone, Airtel, Jio, these are the some of the telecom service providers are there in our country. Fine. And then we have a next 12 ends. Okay. So this is actually the account ID or the SIM number. Fine. And this is some sort of information which will help the service providers to uniquely identify you. Okay. You in the sense means the SIM card holder. Fine. And then, as I said, C is the checksum, which will be calculated by using this particular thing. We also have some extra, let's say the 20 digits, which is represented by this. And this is returned by using this particular command, but it is not officially the part of the ICC ID. Fine. Now, if I'm talking about, let's say the SIM. So if I'm saying that, because we should understand the difference between the SIM and the USIM. So if I'm talking about a SIM, I'm saying that SIM is an application on the, okay, and UICC, which means the universal integrated circuit code. Fine. Which is here. Okay. And so, earlier UICC was called a SIM card because this was the only application available on the SIM card. And as you can see, what will be there inside that? So you will find this kind of information in that. Fine. Then USIM came in the picture. So USIM is a kind of mini computer, I can say that, because it can handle several mini applications. What are those mini applications are there? Such as a contactless, let's say the purse of underground, let's say the trains, a local service portal giving you access to your phone bill, fine, etc. And regarding security, a new algorithm is integrated. Fine. So this protects you from unauthorized access to your phone line and therefore being charged with fraudulent call on your bill. So your call and data, let's say, exchange are encrypted using the key compound by using the USIM, and which are stronger than those provided in the SIM. Fine. And there are some other features also in the SIM. So the SIM and USIM, if I'm saying that, so if I'm saying that ki SIM and USIM, so they have two different piece of information. Okay. And they contain information which is different. So when I'm talking about, okay, what sort of file structure is followed or file system is followed in the SIM card. So as I said in my earlier, let's say the earlier slides, earlier presentation, this SIM card is organized into a tree hierarchy. Fine. So if I'm saying that tree hierarchy, so this is the tree hierarchy which is there. Now in this tree hierarchy, we will find a master file, which we can also call this file as a root file. This master file contains several, elementary files and the dedicated files. And dedicated files and this MF corresponds to directories, and EMF files corresponds to file. Fine. And which are, let's say, the analogous to hierarchy in any common PC operating system. So these two hierarchies differs in that DF, which is dedicated files, can also contain data. Fine. And DEFs, EFs, and MF contains security attributes resembling the user right associated with a file or directory in a common operating system. Fine. So any application can traverse the file tree, but it can only move to a node if it has the appropriate access right. So when I'm talking about the access right, which means, I'm talking about the authorization. So this is the another security property which is very much required, because this security property, guides or tells us an application what this particular user can access from this application. And this authorization comes immediately after the authentication. And authorization is only possible after the authentication, because authentication uniquely identifies a user by asking a user ID and then ask user to prove that this ID belongs to you. Fine. So once the authentication is done, then the authorization comes in picture, takes the user ID, and then finds what are the files or the directory this user can access. And then the access of those files and directly will be given to the user, which means the user will be able to traverse only up to that and can access that particular information. Fine. Okay. So in this way, this SIMs typically manages the files and the directories. Now, when we are talking about access right, so basically there are 5 types of access rights to a file, and the file can be DF file or it can be EF file also. Fine. And then some operating system, provides further labels also. So I have not included those. I'm just talking about the 5 labels. So those 5 labels are as follows. Number 1, ALW. Here ALW stands for always, which means access to the files can be performed without any restrictions. So that is why in the authorization field, we have one more security property, which is named as least privilege, which means, let's say, if you want to access some functionality, you must require the access of some of the files. Fine. So then the access of those files must be given to you. Otherwise, you will not be able to access that particular service. And if you will not be able to access the service, you will not be able to perform the various tasks. So I will take a simple example. Let's say if I'm talking about myself, so I'm associated as an assistant professor in the computer science department. If I want to access any files related to my departments, then I should be given assistant professor role in the computer science department at the NITK. Then only I will be able to access it. So similarly, here also the sum of the files whose access is required. So then as per the least privilege principle, we will make sure that those access will be given to the files without any restriction, and the access of those files is required to all the users, let's say. Another thing comes here is card holder verification 1, which is named as CHV1. Fine. So this CHV1 again says that here the access can only be possible when you will provide a valid CH1 value. Fine, which means, let's say I'm talking about some sort of pin based authentication. So if you want to access this information, you authenticate yourself, and in order to authenticate yourself, what you are supposed to do, you are supposed to provide your pin number. Similarly, we have CHB2 also. So here they are saying that access can only be possible when a valid CHB2 value is presented. The fourth one is administrative, which is represented, abbreviated as ADM. So this speaks about the allocation of these labels and the respective requirement for their fulfillment are the responsibility of the appropriate administrative authority, which means the administrative authority will define, let's say, who can access what. And the last one is never, which is abbreviated as NEV, means access to file is forbidden. Fine. So these are the some of the access rights are there, which you will find in this kind of, let's say, the file system. So now let me come to the same USIM, because the USIM which we are inserting in our, let's say, the mobile equipment, we should know what is present in this SIM. Because, now I'm trying to address the issue is, let's say you are supposed to authenticate yourself to the, let's say, the service provider, and as well as the service provider also are supposed to authenticate itself to you. Now, what is the reason of that? Otherwise, what will happen? Somebody else will sit in between and will try to pretend like you, or maybe like a service provider. Fine. And then what will happen? We will end up with disclosing our information to the unauthorized access. So in order to overcome that particular scenario, we require some sort of information with the user in the SIM. Fine. And then we will make use of that particular information in order to perform either one-way authentication or the mutual authentication. So let's say if I'm talking about, let's say we all are doing the e-shopping and all, e-commerce shopping and all. So whenever we are typing amazon.com or flipkart.com, what is happening? A reply is coming to us. Okay, and then there is a certificate associated with that, and that certificate ensures us, hey, look, whatever the reply you have received, this reply you have received from the Amazon server only, not from any other server. Fine. Now, why we require that? Why we require the authentication of the service provider? Otherwise, what will happen? We may end up with using somebody else, let's say the service, and that somebody else may be the attacker and may be interested to steal our, let's say, the browsing statics, so that he can sell that statics to somebody else, or he can gain the access, or let's say, or he can design some sort of strategy, and by using that strategy he can design some sort of phishing attack, and then he can, let's say, steal our some sort of information, or he can make us to, let's say, provide some sort of information. So in order to avoid all those things, what we require the USIM. So USIM, or the SIM which is there, so whenever we are buying this particular SIM, so inside the SIM, you will find a public key of home. So the question comes, so we are purchasing a SIM from a particular service provider. So what this operator does, they creates a key pair, which is named as a public key home and the private key home, which is represented here as a PUK home and PRK home. Fine. As we all know, public private key concept. Private key supposed to be private, should not be disclosed to anybody, because if it is disclosed, then most of the security properties which we can fulfill by keeping this particular key securely will not be able to. So then what operator does, it generates a key pair for a SIM card, and then what he does is the public key. Public key is a key which is supposed to be available to, let's say, as and when it is requested. So then what it does, it inserts that public key of home inside this particular SIM. Now, apart from this, what else we have? We also have some other piece of information. So what is that particular information? So we also have a generator inside the SIM. Okay, and what this particular generator will do? So this generator will generate a key pair which is named as a ephemeral public key and the ephemeral private key. Apart from that, we also have a key K which is named here as a long-term key. Obviously, the operator will generate and put this particular key inside this. Then what we have some functions. These functions are required. So function F1 is required to perform the encryption decryption. Similarly, the function F2 is required to calculate the hash or the message digest of a message. Then we also have some sort of information which is named here as a, let's say, the IMSI. Fine. A information. Fine. So which is very much useful, and with the help of this particular information, we can uniquely, let's say, identify entity. So now once this SIM is there, so as you can see now something is there inside the SIM which is named here as a IMSI, fine, and oblique SUPI. So what is this? So IMSI is International Mobile Subscriber Identity. Now what is this SUPI or the SUKI? Because before getting into that, we should also understand what is this SUPI and the SUKI. Right? So this 5G authentication framework, what it does, it makes use of the subscriber or subscription identifier. Fine. So if I'm talking about piece of information, so what is there in the IMSI, if you'll see, so this IMSI, which will be of 15 or 16 digit, consists of MCC, which is mobile country code, MNC, which is mobile network code, and then what we have up to 10 digit MSIN. Here MSIN stands for mobile subscription identification number. Fine. So if I'm talking about what is SUPI, okay, so if I'm saying that for 3GPP, IMSI is SUPI. And if I'm talking about for non-3GP, then NAI will be equivalent to SUPI. Fine. So the question here is, some of you can ask is, why we need to require SUKI? Why not IMSI is sufficient? So when I'm going to talk about, let's say, the key management technique, which is used in 4G LTE, they're actually using IMSI instead of using, let's say, the maybe SUKI or SUPI. Fine. Fine. So we will see there. So now the question comes here is, if we are creating some sort of information, something like this, fine. So what is that particular information? How this information will help other, and how this particular information is organized? So we have, when we are talking about the SUKI, okay, so SUKI stands for subscription concealed identifier. So in the SUKI, you will find the SUKI type. Fine. So if it is 0, value is in between 0 to 7. So if it is 0, which means the SUPI is, this is for SUPI. Fine. If it is 1, which means this is for NAI. Okay. And 2 to 7 are for future use. Okay. And for home network identifier, so again, this value depends on SUPI type. Okay. And mostly what you will find here is the mobile country code and the mobile network country code. Fine. Then 1 to 4 digits are there, which includes the routing information. After that, which type of protection scheme is used? So there are two types of protection scheme. One is named as a null scheme. Another one is named as a ECIES scheme. So these are the two protection schemes are there. So which protection scheme is used? So the ID will be present. Okay. And then the home network public key ID will be there. And then the protection scheme, let's say the output is there. And this will depends on the which scheme is used here. Okay. Now, when I'm talking about, let's say, so this piece of information, so how this particular piece of information is generated, fine. So if I'm talking about generation of this piece of information, so let me come to this particular diagram and then I will go back to the previous slide. So basically these 1, 2, and 3, these are the steps only. So here what we have is we have a ephemeral key pair, fine. So this ephemeral key pair generation, fine, what we have a ephemeral public key and ephemeral private key. Okay, so ephemeral, this key generator will generate ephemeral public key and the ephemeral private key. Now this ephemeral private key, fine, and the public key of home network will be passed as input to the key agreement, and then this will generate an ephemeral shared. Then this ephemeral shared key is passed to the key derivation function, and this key derivation function will generate ephemeral encryption key and ICB, as well as it will also generate an ephemeral MAC key. I will cover the key description function in detail later. Okay, and then this ephemeral key and ICB so will be used to encrypt the information. So plain text and is passed along with this key, and this will generate a ciphertext. Then we are calculating the hash of it by using the MAC function and ephemeral MAC key, and this is named as a MAC tag value. So here what will happen? So what is a plain text here? So plain text will be SUPI, and this will be converted into the SUKI by using this particular encryption algorithm. Fine. So that is what is present here. If you see here, it talks about the subscription concealed identifier, how the SUKI is generated. So if you see here, what we have MCC, MNC, MSIN this there. So what we are generating is we are using this ECIES. So ECIES stands for electric curve integrated encryption scheme. I will not get into it because I know so many mathematical things are involved and most of you will not be able to get in just one single session. Fine. So better not to get into it. And as I said, what will happen? So the encrypted MSIN will be generated, and then the MCC and MNC is appended with it. So this piece of information is known as SUKI. Now, once you have generated a SUKI, so at the other end, what we need to do is we need to deconceal it in order to enable SIDF or maybe some other entity to make use of this MSIN number. So fine. So then again, what we are doing is we are going to perform this deconcealment process. Here, what we will do again, we are going to pass this ephemeral public key of UE and the private key of HN, fine, to the key agreement algorithm. And this will generate a ephemeral shared key. And then we are passing this to the key distribution function. Then the key distribution function will generate ephemeral decryption key, comma ICB, and the ephemeral MAC key. And then by using this particular decryption key, we can get the, let's say, the plain text, because we are passing this key and ciphertext as the input. And then, you know what we will do? This ciphertext will calculate the MAC of this, and then this value we can compare with the, let's say, the MAC value which is received in the previous mail to check that whether this particular message integrity is intact or not, or was intact or not during the transmission and at the end of, let's say, or at the receiving end. So in this way, you know, this IMSI information which is there, you know, is converted into the SUKI, which means this information is concealed, and there is a reason behind concealing this information that I will reveal after, let's say, this. So now if I'm talking about, let's say, the access type. So what are the possibilities we have? As of now, still in case of some of the operators, what we are still using our 4G network. Means we are talking about non-standalone implementation where, you know, the 5G radio signals are transmitted over the 4G network and all. So what are the possible access types we have? As this diagram I have taken from core network presentation of Sri Ashok sir's PPT. Fine. So this particular diagram speaks about the possible way to connect to the 5G core network. Fine. So an LTE, an NGRAM, and non-3GPP, how they can connect with that. So now the question here is, when we are talking about the connection, which means what we need to talk is we need to talk about how they will be able to authenticate each other. Authenticate each other in the sense means I'm talking about how the let's say the operator will be able to authenticate the user equipment, how user equipment will be able to authenticate the author, let's say the service provider, because this is very much required in order to make sure that I am communicating with the authorized authenticated person only, not with the XYZ who is acting as the authenticated person. Fine. Okay. So now if I'm talking about this particular piece of information, so which is here represented here. So if I'm talking about, let's say, so how this can be met. So the question here is, so in order to achieve this, you know, in the 4G, we are using, let's say, a mechanism by using which we can ensure the security. So this particular scheme is named as EPS AKA. Fine. So if you see this EPS AKA encryption mechanism, fine. So here what happens when the user wants to access the LTE network, fine. So what the user will do, so here the RRC connection will be set up between the user equipment and the ENB, fine. Okay. So as you can see here, so once this RRC connection is set up, now next, what will happen? The user equipment sends an attached request, which will be some sort of NAS level message to this MME. Fine. Okay. So this is some sort of attached request message. And as you can see inside this message, what is present? The IMSI is present. Okay. Fine. Now, user equipment security capability information is also present inside this, because this information is used by the network to indicate which security algorithms are supported by the user equipment. So let me come back to HTTPS. We are using TLS protocol nowadays to do the secure communication between the web browser and the web server. Fine. And before starting the secure communication, what we used to do? We used to do the handshaking, which is a 4-phase process. And in the handshaking process, what we need to do is we need to identify the algorithm, which, let's say, a highest algorithm or highest, let's say, we used to call there as a we used to call, okay, so a kind of, let's say, a cipher suit. That cipher suits contain the information about the algorithms, information about the highest level of algorithm which both the party can support in order to have a secure communication. So similarly here in this case, what will happen? The user security capability will enable, let's say, the maybe to the network to identify which sort of algorithm should be used, let's say, in order to, let's say, generate the further information, so that once the information reaches at the user equipment end, the user equipment will be able to make use of this piece of information. Fine. So now what will happen? The step 3. So in the step 3, what happens? This MME sends an authentication data request message with IMSI. So inside this, as you can see here, is IMSI, which is provided by user equipment to MME. Then network type is also there, and as well as service network ID is also present in this. Fine. So this piece of information is present, and this MME sends to the home network. Fine. Okay. So now AKA challenge generation at the home network begins with this step 4. So this step 4, okay, which is named here as HSS/AUC, using cryptographic functions. As you can see inside this box, some cryptographic functions are written, which are named as F1, F2, F3, F4, F5. So these are some of the cryptographic functions are there, and these functions will be used to compute a MAC code. Fine. So what we are passing as an input to this, we are passing a key K, a random value is there. Fine. And then AMF is there. And then we have a sequence number. Okay. So these values we are passing as an input to these functions. And then these functions are going to generate or compute a message authentication code, which is named here as a MAC. Fine. An expected response, which is named here as a XRES. Okay, is also going to generate a key, which is named here as a CK. CK stands for the cipher key. Okay, a key, which is named here as IK, named as IK stands for integrity key. And we are also going to get an anonymity key, which is named here as a AK. Right? Okay. Now, if you see, fine. So now HSS oblique, let's say the AUC, using the key derivative function. which is named here as a KDF. I will describe the KDF later in detail. Fine. What it does is it computes the KASME. Fine. So K stands for, let's say, the key. And when we are talking about, okay, so we will be, let's say, calculating. Okay, fine. So this particular key. Okay. And if you see what are the things are passed as input to this. So we are passing a sequence, let's say service network ID, CK, IK, and here you see this sequence is there, SQNet is there. This is concatenated, fine, XOR with the AK, and this piece of information is passed. So here, you know what will happen? A KASME generated, fine. So then we are going to generate authentication, let's say the token AUTN, and this AUTN will contain the concatenation of three different pieces of information: SQN, XOR with AK, AMF, and MAC. And apart from that, we are going to generate the authentication vectors, and these authentication vector will contain a random authentication token, XRES, and then KASME. Right? And then in the step 5, you know, these generated EPS authentication vectors, which are containing 1 to n, they are containing this information such as the random authentication token, XRES, and KASME. They are sent in an authentication data response message from home network to the serving MME. Fine. Now, as there are multiple EPS authentication vectors are there, so MME stores them, and then fine, selects an authentication vector from that. Now in the step number 7, what it does it, now MME sends a user authentication back, let's say the request message to the UE, fine. So I can say the USIM via ENB, and in this, what will be there? A random challenge is there, which is named as a RAND. Then the authentication token is there for the network authentication from the selected, let's say the authentication vectors. And it also includes a key set identifier, KSI, fine, ASME for ME, because it has to identify which key is used. Okay, so which this will be used to identify KASME, fine. And then, you know, what happens at the serving at this the user end. So now the user end, with the help of this piece of information, we will authenticate the serving network. So now the UE will be able to authenticate the serving network by performing this step number 8. So once UE receives this particular message, what the UE will do, or the USIM will verify the freshness of the authentication vector. Okay, by checking whether this AUTN, which is their AUTN, okay, by checking that whether AUTN can be accepted or not. Okay, now what is going to check inside the AUTM? So what it will do is UCM first computes anonymity key AK, fine. And then what UCM does, it retrieves the sequence number from the AUTN, fine. Now, if I'm talking about the AUTN, as you can see here in this side, in the AUTN, we have a 3 piece of information concatenated to each other, fine. So if we will XOR AK, which USIM has generated at its own end, with this piece of information, which is SQN XORed with AK, then you know what we will get the sequence number, fine. And then we can compare, fine, this. Okay, so now then USIM computes expected message authentication code, which is XMAC, as you can see here, fine. And then compares this XMAC with the MAC, fine. So where the MAC is present in the AUTN, MAC is present. Okay, so whichever the AUTN is sent, so that MAC is checked, fine. Next, if the MAC comparison is successful, then USIM considers the integrity check. Fine. So now to okay. So in this way, USIM performs this. USIM also maintains an array of previously accepted sequence number. So this array of previously accepted, let's say the sequence number will help this USIM to identify whatever the, let's say maybe whatever the message we have received, whether really it is a fresh message or it is a replay message, because replay attack is one of the attack in which, what the attacker does, they captures packets and then they keep this packet with them, and then whenever they find an opportunity, so opportunity in the sense means, let's say a session is ended from the user end but it is not actually ended from the server end, then they make use of this opportunity and then they replay these kind of packets. And if we do not have any mechanism at the server end to verify that the received packet is a fresh packet or is already used packet, then server may end up giving unauthorized access to the, let's say, the unauthorized user. So now to verify that the received sequence number is fresh, what the USIM will do? USIM will compare the received sequence number with the sequence number which are present in the array. Fine. And they are indexed by using the index value, which is named as IND. Fine. So once this verification is successful, fine. After this, the USIM computes a response, RES, which is here. Fine. Okay. The USIM also computes, as you can see here, CK and IK. Fine. And then uses this CK and IK as well as service network identity. Fine. And then exclusive or information of SN and AK. Fine. To derive the key, KASME. Fine. And once this key is derived, okay, and this will help, let's say, or this entire process will help the user equipment to authenticate the, let's say, the serving network. Why? Because as you see here at both the end, what has happened? The key will be same, okay, which is generated by using this. So then what happens? Now the user equipment sends the user authentication response message, which includes computed RES to the serving network. Fine. Now what the serving network will do? So the MME check will check that the RES is equal to XRES or not. If so, then the authentication is successful. Fine. So here, what will happen in this way, so this step number 9 and 10 enables serving network to authenticate the user equipment, where the serving network will send RES and then MME will generate, let's say, we'll check that whether this RES is let's say same as XRE equal to XRES or not. Whereas the step number which are present here in the 4, 5, 6, fine. These steps are there for AKA challenge generation at the home network, and the step number 8, which is this particular step enables UE to authenticate, let's say, the user equipment. Now, once let's say UE is able to authenticate user equipment, user equipment is able to authenticate the network, and network is able to authenticate the user equipment. So now the next thing which comes in the picture is the NAS, non-access strum security. This particular security is designed to securely deliver the message between the user equipment and the MME. Fine. Over the radio network. Fine. Okay. So then what will happen? This UE, fine, will, and as well as you can see MME. So what they will do is they will generate the integrity and the cipher key independently and then use those keys for secure transmission of NAC message. Fine. So here integrity protection is made mandatory by the 3GPP specification 3, while ciphering is offered an optional functionality for the NAS message. So let us see how it is achieved. Okay. So now what is happening in the step number 11, as we can see here, the MME selects the NAS integrity protection and encryption algorithm depending on the UE security capabilities, fine, which is received from the UE in the step number 2. And then this, okay, will allow, okay, fine. So, and then they will configure the allowed list of security capability of the current serving network, fine. So step number 2, which is the NAS key generation. So here what will happen? So here now MME generates the integrity key, fine, which is named as KNASINT. So what is happening here? KASME is passed as input to KDF along with the, let's say, the NAS integrity algorithm, fine. And this KDF will generate KNSINT, fine. Okay. So the which will be of 256 bit. Okay. Now MME also generates a ciphering key, which is named here as a KNASENC, okay, which is again of 256 bit. Okay. Now, once these two pieces of informations are generated at the MME end, so then what happens? The security mode command message, which is named here as, okay, so security mode command, let's say the messages is generated at the MME end, and a corresponding NAS MAC for the integrity is also computed, fine, with integrity key KNASINT, so that, you know, UE is assured that the algorithm selection was not manipulated by the attacker, fine. UE security capabilities that UE has communicated to the network during the attach procedure are now repeated in the message, fine. Security mode command from MME to UE. Now MME delivers the NAS security command mode with selected NAS algorithm, okay, and then replayed UE capabilities and the key set identifier to the, let's say, the user equipment, fine. Now come to the user equipment end. Here non-access system security. So in the user end equipment end, this sequence message sequence number 14. So this will help NAS key generation at UE. So here what will happen? Now the ME has to verify the integrity of NAS security code message. So what it will do is to bidding down because, okay, so has to verify this. So in order to verify that, what will happen? So again, the algorithm which is used to generate the encryption key and the algorithm which is used to generate the, let's say, the integrity key is conveyed to, fine. And the key is already there. KSMA key is already present at it. So then what will happen? This will generate, let's say, the KNAS encryption and KNAS integrity keys. Now, once these keys are generated, fine, then, you know, what will happen? The UE will respond with NAS security mode complete message, which is both ciphered and integrity protected. Fine. And then this NAS security mode complete message will also include IMEISB, which means International Mobile Equipment Identity Software version. In case the MME requested in it, then it will be included. Otherwise, it is not in the NAS security mode command message. So then the MME will decipher and will check the integrity protection on the NAS security mode complete using the key and algorithm. Fine. And then algorithm indicates. OK, so then in this way, non-access system security is achieved. So sorry. Next, it comes about the access system security. Fine. So this access system security is designed to deliver messages between the user equipment and the ENB, fine, over the radio channel. Fine. So the scope of NAS is between UE to MME, whereas the scope of AS is between UE to ENB. Fine. So if you want to exchange the message securely between the UE and ENB, then the access system security comes. Let us see how it is achieved. Fine. Again, here, as you can see from this, it looks like, the UE and ENB generate some sort of integrity and the ciphering key independently. Fine. Which will be separate key for user plane and the control plane. And then those keys are used for secure, let's say, transmission of the AS message between these entities. And again, here integrity protection is made mandatory. Fine. While ciphering is optional. Fine. So now how it is achieved? OK, fine. So let us see here. If you see this step number 16. So here in the step number 16, what the MME is doing is MME drives or generates key, which is named as KENB, as you can see here. And then this key, and as you can see, this key is generated from 256-bit KASME and uplink NAS count. Fine. Now this key is generated. Fine. Then MME, sends the UE EPS security capabilities with encryption algorithm. Fine. Integrity protection algorithms and generated KENB in the initial context setup request message to ENB. Fine. Now what will happen? So ENB has received this message. Now the AS key generation will happen at this ENB end. So you see the message number 18. Here what will happen? The ENB selects the ciphering and the integrity protection algorithms from the configured list, okay, which has the highest priority and is also present in the user equipment EPS security capability. Then this ENB generates the RRC integrity key, fine, from 256-bit KENB, fine, selected AS protection algorithm and algorithm type distinguishers. ELB also generates RRC ciphering key, which is named here as KRRCENC, fine, and a UP ciphering key, which is named here as a KUPENC. OK, from the KENB and selected AS encryption algorithm and algorithm type identifier. Once these keys are generated, then ENB sends AS security mode command with selected integrity algorithm, fine, ciphering algorithm, and this message is integrity protected, fine, with RRC integrity key. And RRC and uplink UP downlink, let's say the ciphering at ENB starts after sending the AS security, let's say the mode command message. Fine. Now let us come to the UE end. So UE end AS key will be generated. Find the how the AS key will be generated. So again, as you can see here, KENB used. So similar to MME, KENB will be used. Fine. And then the required algorithm will be used to generate KUPENC, KRR CENC, and KRR CINT. Okay. Then what will happen? ME mobile or this user equipment will send, okay, AS security mode complete with integrity protection to the ENB. Okay. Also, RRC and UP uplink ciphering in the UE start. Okay. After sending the AS security mode complete message. Fine. Now, if you see this step number 22, what is happening here? If the attach request is accepted by the network, then what will happen? The MME will send the attach accept message to the UE and UE will respond with the attach complete message. So, this is the overall process of, let's say, the EPS AKA, which is used in the 4G to authenticate, let's say, user equipment to the network to the user equipment, as well as to securely exchange the information, okay, between user equipment to the radio network, to the MME, and to the HSS, and the vice versa. Fine. So now, if I'm talking about some of the, let's say, the vulnerabilities. So as you remember here IMSI is sent in the plain text format. So what is the, let's say, the vulnerability of disclosing the IMSI? Okay, so the vulnerability which will be associated with the disclosure of let's say the IMSI is the will affect the, let's say, the user confidentiality. So the question comes, how it can affect the user confidentiality? Fine. Somebody is unmute, kindly mute yourself. Okay, fine. Similarly, various other security issues are there in the 5G AKA. Okay, so if I'm talking about, let's say, the so these security issues, fine. So I'm saying that if the IMSI is disclosed, fine, there can be some sort of, let's say, the vulnerabilities associated with it. So one of the problem of the IMSI disclosure will be the theft of the service with session mix-up attack. Fine. And this can be an inside attack where attacker is a subscriber of the network. And what will that particular attacker will do, which is a subscriber of the network, will impersonate itself as another subscriber. Fine. To use the service that the victim should get from the network. Fine. So the disclosure of IMSI, as I hope so you all can understand the, let's say, the what will happen if the IMSI is disclosed. Like that, so many other problems are there. Okay. So in order to solve this, one of the solution is to not to disclose this particular information. So not to disclose this particular information in the sense means conceal this information, and as and when is required, deconceal this particular information. So that is why, this SUPI and SUKI came in the picture. So the IMSI is concealed, and when it is required, it will be deconcealed. Okay. Apart from that, various other attacks are also there. These attacks are there in case of, if I'm talking about this EPS AK, these are the some of the vulnerabilities. Okay. So if I'm talking about vulnerabilities, one is the IMSI disclosure. Another one is GUTI persistence, sequence SN ID disclosure, service network ID disclosure, and then, acceptance of TAU reject service reject, and attach reject message without integrity protection. So these are the some of the vulnerabilities are there. Similarly, UE network and security capability disclosure and the synchronization failure. So these are the some of the vulnerabilities are there which are present in this EPS AKA attack. Now this vulnerability attracts what kind of attack? So if I'm talking about IMSI disclosure, I said impersonating user equipment. Fine. And just now I have given one example. Let's say if an user which is the part of the network and impersonate another user which is also the part of the network, then what will happen? That particular user will be able to breach the confidentiality. Fine. So this IMSI disclosure vulnerability attracts impersonating attack, impersonating user equipment attack. And the goal of this particular attack is to weak the subscriber confidentiality. Fine. Another one is GTI persistence. So the attack associated with this is man in the middle. Man in the middle attack. Fine. And the goal of this particular attack is to, let's say, hinder the availability of the HSS and the MME by performing some sort of distribute of service attack. If I'm talking about SN ID disclosure, so the attack involved is fake ENB, E node B. Fine. And then what will happen if fake E node B is there? And if we are communicating with the fake E node B, so the attack goal will be to disclosure of the, let's say, the subscriber location, beat the user equipment data security, and then intercepting the connection between the user equipment and the network. Fine. And then the denial of service attack. Okay, fine. So these are the some of the, let's say, the attack goals are there. Similarly, let's say if I'm talking about user equipment and the security capability disclosure, then this will attract bidding down attack. And here the attack goal will be perform some sort of denial of service attack against a user equipment. So the question comes here is, if this is the case, then how all these are protected? So we have some way by using which, we are making sure this attack should not happen, but still there are possibilities of these kind of attacks. So how these are improved? Let's say in case of 5G. So as we know, this new generation radio access NG and NGRN. So here we have two authentication methods, fine, that are supported in user equipment and the service network in 5G, which are named as EAP AKA, fine, and 5G. So EAP AKA dash, which is also known as EAP AKA prime, and the 5G AKA. For a private network which is using 5G network, a 5G system, the additional authentication method which can be used is EAP TLS. Fine. So now, I'm going to talk about brief. I will not, let's say, take here much time because, it is very difficult, hard to, let's say, digest. But what I'm trying to convey here is the sum of the difficulties which we have identified in the earlier case, we are going to overcome those difficulties and we will try to protect the securities. So with the help of this, we will try to identify how this mutual authentication, confidentiality, and the integrity, as well as the authorization, is ensured in this 5G communication, as well as what are the network functions will be involved in order to, let's say, perform this service operations. So we said, if I'm talking about 5G authentication framework, fine, as you can see here. So 5G authentication framework basically involves from the user equipment side. Fine. So user equipment oblique USIM, and from AMF oblique SEF side, service network. Fine. And AUSF and UDM, ARPF, and SIDF from the home network side. So if I'm talking about AMF oblique SEAF in brief, so here SEF stands for security anchor function. And as we all know, this particular function provides authentication functionality via the AMF in the serving network. Fine. And this SEAF supports primary authentication by using the SUKI. We will see. Fine. Then we have AUSF here. This is so AUSF stands for authentication server function in the home network, and this handles authentication request for both in the sense means for 3GPP access and non-3GPP access. So AUSF handles that. AUSF provides 2P to the visited PLMN only after an authentication confirmation if the authentication request with SUKI was sent by visited PLN. Okay, so this AUSF informs the UDM whether a successful or unsuccessful authentication of a subscriber has occurred or not. And if I'm talking about UDF oblique ARPF oblique SIDF oblique UIDR. So long-term key used for authentication and the security association setup are protected from the physical attack, and they are and never leaves the secure environment of UDM oblique ARPF. Fine. So the algorithm used for, let's say, the subscriber privacy is executed in the secured environment of UDM. Okay. And the SIDF, which is here, is responsible for deconcealing the SUPI from SUKI. Fine. When the home network public key is used for the encryption of the SUPI. So SIDF uses the network home network private key, okay, which is securely stored in UDM to decrypt the SUKI. So the UDR user data repository supports the storage and the retrieval of subscriber data from the UDM and the policy data from the PCF. SUPI and the SUKI I have already, described in the previous, let's say, the slides. Fine. So now let me quickly come to the 5G AKA procedure. So if you see this 5G AKA procedure here, what is happening is now when the user, let's say, wants to access the 5G network, so what will happen? This user equipment will perform the random access procedure, and RRC connection is set up between the user equipment and the GNB. Fine. At the ME, what will happen, or the USIM, the SUKI concealment is performed. Fine. So then the UE sends either the SUKI or 5G G2EI if assigned previously in the registration request. As you can see here, instead of sending the IMSI, now what we are sending is SUKI, and SUKI is the concealed IMSI. Fine. So now in this way, we are able to protect the IMSI disclosure. And if we are able to protect the IMSI disclosure, which means we are able to increase the confidentiality. Okay. So now then what will happen? What this AMF oblique SEF initiates the authentication. Fine. By sending the authentication request, as you can see here. And what is there inside that? SUKI or SUPI is there, and this serving network name is there. Fine. Now this AUSF checks the receipt, let's say this serving network name with the expected service network name. If authorized, fine, then this AUSF sends the authentication get request message. Fine. What is there inside this? Either SUKI or SUPI will be there, and SM name is there, and the service network name to the UDM. Fine.
50 minutes reserved for solving all the questions, sir, quickly. Last 10 minutes for
kindly mute yourself. Okay. Now when we are coming to the step number 5, which is here. So as you can see here, what will happen? Now the UDM will invoke the SIDF. Fine. And if SUKI is received, then what the SIDF will do, will deconceal SUKI to gain the access of SUPI. SUPI is IMSI before UDM can process the request. Now, based on this SUPI subscription information, the UDM will give the input or invoking the authentication method. Okay, which means which authentication method supposed to be used, such as 5G AKA, EAP AKA prime or EAP TLS by the AUSF. If UE has USIM, so then the 5G AKA or EAP AKA prime can be used in any network. And then key generating EAP method such as EAP TLS was introduced in 5G for non-public network. Okay, fine. So now what will happen? Come to this home network, step number 6. Now we are going to generate the authentication vector. So again, as usual, quickly, here the authentication vector is generated, as well as we are also generating the 5G HEAB, in which we have a random, we have an authentication token, we have a XRES fine, and then we have a KUSF. Okay, so all this is done. And then if you see what is happening, the home network, fine. So UDM and ARF sends the authentication get response message. Inside that, as you can see, 5G HEAB is there, SUPI is there, fine, and AKMA indication is there, fine. If the AKMA subscription is present, then only the AKMA indication will be there to the AUSF. Now what the AUSF will do, AUSF stores XRES and calculate the hash of that, which is named here as a HXRES. Fine. How it is calculated? So, okay, and then generates, let's say KSE AF using the this derivative function. Fine. Okay. Now AUSF sends the authentication response message. Inside the authentication response message, what we have is we have the 5G serving network environment authentication vector, fine, which contains random authentication token and XHRES star. Now what will happen? This serving network. So AMF SEF will store this received hash expected response, fine, and then will send the authentication request, which contains random, fine. Next, key generation identifier, NGKSI, fine. Anti-bidding down between architecture parameters in NAS message, fine. Authentication request to the UE. Now, once UE receives this, now the network authentication will be done by the UE. How? So this particular thing comes here in the picture. Here, once the UE receives this message, now USIM will verify the freshness of authentication vector. How? By checking whether the AUTN can be accepted or not. And for that, what he has to do? He has to generate AKN. Fine. XOR with this, SQN will get and see whether that is same as of not. Okay. Fine. If verification is successful, then USIM will also compute a response RES. Fine. And USIM will also compute CK, IK, okay, which are sent to ME. The KUSF, RES, like XRES generation, and KSEF are computed at the user equipment end, similar to the generation of UDM and ARM. Then what will happen? This UE responds with RES in NAS message authentication response to SEAF. Okay, so message step number 13 and 14 are the part of network authenticated by the UE. Now, step number 15, 16 will enable serving network to authenticate the user equipment. How? So what the serving network will do once it receives, okay, message, the serving network at the step number 15. So AMF/SEF will compute HRES star. So we'll calculate this and then we'll compare this with the HXRES. Fine. Authentication considered as successful from the service network point of view if the compared values are equal. Then what will happen? This AMF or SEF will send RES, fine, as received from the UE to AUSF. Fine. Now what will happen? Here, home network will authenticate the user equipment. How? So see the message number 17. Fine. So AUSF will consider the authentication is successful when if the RES star is equal to the stored and expected response from HREX star. Fine. Then what will happen in the step number 18A? So 18ES has two things, 18A and 18B. So now this AUSF will send an authentication response to the AMF/SEF. This will contains the result, SUPI and KSEF. Fine. And then what will happen? It will also send an authentication result confirmation request to the UDM. Okay. Fine. And here in the step number 19, SEF generates the key KMF, okay, with received KSEAF, okay, IMSI and ABBA parameter. And then SEAF shares the generated KAMF and NGKSI to the MF. Fine. And then this step number 20 and 21 are required to store this authentication results. Fine. So then what will happen? The UDM will store the authentication status, okay, of the UE, and UDM replies to the AUS with the authentication result confirmation response message. Fine. So this is the overall process which is involved in the 5G AKA. Fine. There is another protocol which is named as a 5G AKA dash, or we used to call as a 5G AKA prime. Fine. So this 5G AKA prime, okay, so we can say it is okay. Fine. So if you see more or less this particular protocol contains the steps. Okay. So if you see the step number 1, 2, 5, they are same like which we saw in the previous case. Fine. And then step number 6 starts from the home network, where the home network computes, as you can say, AKA challenge vectors. Fine. And then, if I'm coming to step number 9 here, what happens? Network authenticated by user equipment. Okay. And then step number 11, 12, 13 and 14. Fine. They contributes towards the user equipment authentication at the home network, which means they enable home network to, let's say, authenticate user equipment. Fine. Okay. So if you watch carefully, with the help of these protocols, what we are trying to ensure is we are making sure that wherever the user equipment authentication is required, there is a process which will ensure the authentication of user equipment, and wherever the authentication of maybe the serving network or the home network is required, there is a process which will enable, let's say, the needing, let's say, the entity to perform that particular step, as well as the information which is getting exchanged between either the user equipment, serving network, or the home network is encrypted or by using the, let's say, the key which will ensure the confidentiality and the integrity of the information. Apart from that, we also have okay, EAP TLS. Fine. So this EAP TLS, as I said, this is another protocol. And if you see more or less again here, what we have a required number of steps. OK, so with the help of this step, what we are trying to do is, if you see the message number 1 to 8, with the help of this message number 1 to 8, we will try to, let's say, securely exchange the SUPI. Fine. Whoever is needed that SUPI. Then if I'm talking about, let's say, the message is starting from 9. OK. So this ninth message, which is there in this, will again help us, OK, UE to authenticate network, whereas this message number 10, fine, will help network, OK, to authenticate UE, fine. And then, we have some key generations in between which are required, OK, and as well as the response of authentication and the confirmation of that. So these messages will be exchanged in order to achieve that. Okay. So similarly, when we are talking about, let's say, the untrusted and let's say the trusted non-3GPP access. So if you see this particular piece of, let's say, the this particular diagram. So this particular diagram again speaks about the authentication which is there in place for the untrusted non-3GPP access. I have also have one more diagram. This particular diagram talks about the trusted non-3GPP access network. Fine. So again, if I'm talking about, let's say, the detail of this particular diagram, fine. So I will say in general what we are trying to, let's say, achieve with the help of this particular diagram. So basically, you know, we want to make sure that whether it is a untrusted non-3GPP access or the trusted 3GPP access, fine. How a UE is authenticated to 5G network by using a untrusted non-3GPP access network. Fine. Again, so here, what sort of, let's say, the security feature will be used? So we can say here we are going to use some sort of vendor specific, let's say, the method, okay, which is also known as EAP 5G. Okay. So if you see, let's say, this particular diagram, which is which talks about untrusted. So if you see in this particular diagram, so when a UE user equipment wants to connect to an untrusted non-3GPP access network, okay, with procedure outside the scope of 3GPP, fine. So what UE decides to attach to when I will say the UE decide to attach to 5GC network. So what the UE will do, you will select an N3IWF in a 5G PLMN. Okay, and then the UE will proceed with the establishment of an IP security association. So a tunnel will be set up, fine, within the selected N3IWF by initiating an IKE, fine, Internet Key Exchange. This is a protocol, so which will do the initial key exchange and all. Fine. Again, so actually there are so many steps are there in this. So basically, again, with the help of this, we will try to ensure, in simple what I will say, the authenticity of the communicating entities, the integrity of the information getting exchanged between them, the confidentiality of the information getting exchanged between them, as well as the authorization of the information. Fine. So these are the some of the properties are there, security properties are there, which we will try to ensure with the help of this kind of network. So when I'm talking about the authenticity and the integrity, which I have talked about in this particular, let's say, the scenarios, whatever there in this, or maybe which is present in this particular diagram. Let's say when I'm talking about the encryption and decryption. So obviously for the encryption and decryption, we are generating a key, fine, which we used to call as sometime a session key if the symmetric key is used. And then we used to use that particular key along with the encryption decryption algorithm, fine, to generate these ciphertext and decipher that particular ciphertext in order to get the plain text from that. Okay, so with the help of this particular, let's say, the protocols, we are trying to ensure the security. Now, when I'm talking about the security, so here, what I'm trying to do is I'm trying to talk about the secure association of user equipment with the service provider. Now, let us assume that once this user equipment is associated with the service provider, fine. If the service provider contains the network slices, which means the service provider has virtually partitioned its radio network, then what will happen? Not all user equipment will be allowed to access all the network slices which are present in the, let's say, the subscriber in service provider environment. Fine. So now how to handle this particular scenario? So that falls under the, let's say, the category of the network slice security. And as the sufficient time is not there, so I will not be able to cover that also in detail, as well as I will not be able to cover, let's say, these authentication for untrusted non-3GPP access and the trusted non-3GPP access network scenario. But I can share the document, technical document. In that document, you will find the information about these two approaches in detail. You may have to make little bit effort just to, let's say, understand in your own way. Fine. But the detailed information is there about each and every step. The key hierarchy in SDM. So I was talking about the KDF. Fine. So we have a two different side. One is network side, another one is the UE side. Fine. So when we started, what we saw is there is a key, which we are calling as a long-term key, present at both the end, at the network side also, as well as UE side also. And then with the help of this key, as we saw, we were generating the CK and IK, cipher key and the integrity key. Fine. This information we can find at both the end, if you remember that particular diagram. Then if I'm talking about the UDM oblique ARF or ME, so at the UDM of ARF, if I'm using 5G AKA, then what we are doing, we are generating KAUSF, and by using EAP AKA prime, if we are using that, we will generate the CK and IK dash, and then we will generate the KUF. Fine. So what will happen if I'm talking about the network side? We have KUSF at the AUSF, and we have KUSF at the ME level. Fine. Then we will generate the KSEF, which will be present at the network side at SEF and user side at the ME. Then from this KSEF, what we are doing, we are generating a KAMF. Fine. KMF can be used to generate KMF also. And if we are talking about, let's say, non-3GPP access, then K3, KN3IWF key will be generated. We are also generating KNA SINT, KNA SENC key, which will be there at the ME level. Apart from that, if we are talking about, let's say, this radio network, the KGNB will be generated and NH will be there. And from this, we are going to generate KRR, CINT, KRENC, KUPNT, and KUPENC, which we saw in the earlier cases. And this particular diagram speaks about the in detail description of the same thing which is present in this particular diagram. Fine. So how the key derivation and the key distribution is done, fine, for the network node. So I'm talking about, this is the network side, network node, how the keys are generated, okay, and distributed. A detailed diagram is there for that. And similarly, the key distribution and derivation for user equipment. So we have a user equipment there. So if you see this particular diagram, this is user equipment side, how these keys are getting generated. So again, same thing is there in detail, fine, which we also saw, let's say, in case of these protocols where I'm talking about the KDF. Okay, fine. So in this way, the keys are distributed and derived in the 5G network for the network node as well as for the user equipment node. And these are the some of the, let's say, the references are there, fine, which can provide you the information about this in detail. So Sanjay sir, that's it from my side for the today's lecture, because there are so many other things which I cannot complete in one class, and bombarding so much information in one class will not be sufficient because most of the participants will not be able to understand that. So that's it from my side, sir.
So thank you.
Great session, sir.
Yeah, thank you, Dr. Mahendra. It was really a wonderful session on 5G security, and I understand you tried covering, even you started with 4G, what kind of security is there in 5G. You tried all akka authentication, EAP authentication, and quite in detail, giving every flow. You also talked about privacy part with SUPI, how that exchange happens and all. So I think you have covered in very, very detail, and the person who knows everything about 5G can only understand all these security aspects. It is very difficult for everyone to consume, but it was really, really wonderful presentation from your side, and you have covered everything. I have one request to you that like we would like to use your presentation if you agree also to upload on a Government of India LMS, Learning Management System, we call it IGOT, so that many other stakeholder in government can take benefit of your lecture. If you agree, then only we'll put it up.
So I have one small request, sir. So can
Yeah.
I, because in this presentation, some of the part I skipped. So can I prepare a video lecture which includes the complete description of each and everything which is present in this slide? And I will prefer to share that video with you. You can use this video, sir, but most of the things are not covered in detail. So I don't have
Okay.
any issue. You can use this
So,
video and
so Dr.
presentation.
Mahendra, then,
Yeah.
Dr. Mahendra, then we would like to go with you the way you request that, like you can prepare a separate one.
Yeah.
And in case you are preparing a separate one, if you can break down into small modules of less than 10 minutes, less than 10 minutes. So module 1 covering say Suki privacy aspects, module 2 covering like in between I was also not in the class, so some portion I actually heard you and some portion I missed, so I don't know. So maybe when you are talking about different new thing which has come, like between the two home network and visited network, we have that N32 interface and security aspects there. When we connect UPF of the two network, you have IPUB. So all those, I mean, you can create some sort of module different. akka procedure you explained very nicely. So akka procedure itself can be one module. I don't know whether in one we can cover or more than one of 10 minutes we can cover. So, but that will take you a lot of time. I don't know whether you'll be able to give or not. So the first thing I would request that let us use this, whatever you delivered today. And parallelly, if you are able to give me a module wise, and then we will replace the current one with the new one which we'll give, so that it is a nicely done presentation. So thank you
Definitely,
so
sir.
much. Yeah, thank you so much. And maybe I can request others if they have any question. Ma'am has opened the video. Ma'am, do you need to ask any question? Dr. T. Pichaiya Saab also perhaps want to speak.
Can I ask one question? It's a general layman question. Okay.
Please, sir, go ahead.
This, yeah, this whatever are the security authentication, is it suppose in user side, user equipment side, it will handle by the SIM itself or any involvement of OS also?
Sir, SIM will do all these things. So in the SIM, we have algorithms which will encrypt, decrypt the information. We also have, let's say, keys, and we also have a key generator in case if we need to generate the key. So entire thing, entire, let's say, the process will be embedded inside the SIM only.
Achha, it's independent of operating OS.
Yes, yes, yes. So that is why this SIM has a kind of operating system which is required, let's say, to process all those information. So we are not going to depend on the user equipment such as and set and all. Because again, if we are doing that, then we are going to open, let's say, various other untrusted path, and we will not be able to safeguard this information from them. So that is why we are restricting to the SIM only.
So all this process should complete to satisfy the requirements of 5G latencies, right, sir? Suppose if you all this process is a part of our latency calculations, there are some latency requirements for 5G, 6G, 4G.
Correct.
So this total process is also part of that latency.
Yes, yes, and we will make sure that whatever the authentication authorization approach is there, that is, let's say, the lightweight, so that it will not increase, it will not, let's say, involve extra overhead, which will increase the latency. So we have to make sure that also. So it is designed in such a way so that it is not going to affect the, let's say, the overall latency of the.
Thank you, sir. Thank you. Over from my side, over. Sir.
Is there any other question?
Sir, I have one question. Hello, sir. Am I audible?
Yes, you are audible, sir.
Sir, actually, what sort of research activities that can be considered in 5G security, sir? Because
Yes, sir.
the well-developed infrastructure you told that has been established. Now, the things of authentication when it comes to algorithms,
Right.
readily set of algorithms are available which have been already implemented. What sort of issues that can be considered to go ahead with 5G security in this concern?
Okay. So, sir, I will answer your question by using a simple thing. So we all know RSA, which is used nowadays. Fine. RSA is one of the strong encryption decryption algorithm. I'm talking with respect to, let's say, the mathematical calculation involved in it. But if I'm talking about the use of RSA in
Yes,
the
sir.
present world by using a 64-bit key, fine, then the same RSA will not be secure, will not be able to provide the security in the present world. The reason behind that is that whatever the key size which we have considered will be guessable, will be breakable, will be, let's say, the generatable in the present environment. So similarly,
Sir, then we'll
these.
go for SHA-256, right, sir?
Yeah, that is why. So that is why, what we are doing, we are not never changing the RSA. Our RSA is same. Whatever the advantage and disadvantage of RSA is there is same. What we are doing, we are increasing key size. Once we are increasing the key size, so we are able to bring a larger key space, a larger key domain, which requires millions of years of time to guess all the keys and then test all the keys. Fine. So what we are doing, we are increasing the key space in that case. Now, when I'm talking about here, the authentication on access control requirement. So let's say we have a well-defined algorithms to securely associate a user equipment with the network, with the service provider. The scenario which I have mentioned here is, let's say once a service provider is going to create network slices, fine, then what will happen? The further security requirements are there, sir. So one of the area is where we can address the security requirements of the network slices. Now, once a radio network is virtually partitioned, so we require some controllers. So we are using software defined controllers nowadays in order to enable the communications between, let's say, two different planes, control plane and the application plane. So when I'm talking about the SDN
Yes,
controller, now SDN controller is using a protocol to enable the communication between these two parties. We used to call as a southbound and northbound communication. Now this algorithm, so one of the algorithm is, okay, fine, I will recall the name. So now these algorithms, no, they have some limited capability. So if I know this particular algorithm cannot hold data more than this size. Now, if I want to hinder the availability of that particular controller, which is there to facilitate the communication between the data plane and the, let's say, the application plane. So then what will happen? I will launch some sort of distributed denial of service attack, which means I will engage the controller, fine, beyond his capacity. Then what will happen? Controller will be engaged by processing some unwanted request. Okay, and then controller will not be able to serve the requested user. So one of the attack which we can address there is the security of controllers by designing a mechanism which can detect whatever the request messages are coming, whether they are genuine or not, whether they are, let's say, some sort of denial of service attack packets or not. Okay, so sir, like that, various areas are there. Similarly, whatever the hardwares we have, such as, let's say, switch, routers and all those things, we are virtualizing them. Fine. So now the NFVs are coming in the picture. Network function virtualizations are coming in the picture. So there again, we have some security issues and all. Okay, so we only have algorithms which can securely associate user equipment to the service provider. And then in between, when we are going to, let's say, utilize or experience the true benefit of 5G, then there are so many other security steps are there which yet to be addressed. So this 3GPP, they have given some sort of guideline to us. They are supposed to be a security, something like this. Now we are yet to design algorithm to achieve that particular security. So a lot of security work is there, which cannot be covered in this. But later, if you are interested in the security issues and all, you please connect with me. I will provide, let's say, all the potential area of, let's say, the 5G security, which require immediate attention in order to make use of full-fledged true 5G, let's say, network in the present environment.
Thank you, sir. Thank you very much. I'll be definitely in touch with you, sir.
Okay, welcome,
Great
sir.
presentation, sir. Yeah, thank you.
So if there is no question further, we should go for the closing thanksgiving to Dr. Mahendra Pratap Singh. I think we should go ahead. So on behalf of the DP team and all the participants, I extend heartfelt gratitude for your invaluable contribution for your faculty development program. Your session on 5G security was very pertinent and contemporary, which would be beneficial in understanding the cutting-edge technology. Sir, your dedication for sharing your expertise and insight has been truly inspiring. Your presentation demonstrated your profound understanding of the subject matter, providing deep insight and a clear perspective that captivated the audience. Your expertise and eloquence were evident throughout the presentation and will enrich our program significantly. We are immensely grateful to have such a distinguished speaker like Dr. Mahendra Pratap Singh of NIT Suratkal. Kindly accept our sincere thanks and gratitude on behalf of all the participants. And special thanks for all the participants also for their active engagement and valuable contributions who made this session fruitful and successful. Once again, I thank Dr. Mahendra Pratap Singh and all the participants. Warm regards. Jai Hind, sir.
Thank you, sir. Jai Hind.